In this video, we're going to see how we can use segmentation methods to identify the objects that are observed in this image, which corresponds to the acquisition of a biopsy of breast normal tissues, where nuclei was stained with DAPI and appears blue, and fish detection of RB2 in green and MYC in red. We're using the two other channels. So we're going to start with the nuclei segmentation. So I'm going to first split the channel. So go to Image, Color, Split Channels. And I'm going to change the color in gray levels so we can better appreciate the contrast. Grays. All right. So I'm going to duplicate this image because I'm going to try several segmentation approaches to see which is the best one. So if I go to process to image duplicate so that I can save one. Okay, so I'm going to work on this one. And I'm going to first use a simple thresholding. So before that, I'm going to filter the image with a median filter. And now just manually threshold it. So if I go to adjust threshold, all right, dark background, and I'm going to try to do the best job I can here. So we're going to use also mathematical morphology, so it doesn't need to be perfect. Then I can just try to improve the results by using appropriate mathematical morphology approaches. So I guess this is pretty good. Let's just apply it. And now we're going to first fill the holes. So go to Image, Process Binary, Fill Holes. And I'm going to apply a binary watershed, process filters, process binary and watershed. All right. And if we compare to the original image, so on top we have this partial nucleus, which is really just a small part of a nucleus, and it's not going to be very informative. So here in a post-processing step, we could just get rid of small structures, and we could get rid of this because this is not going to help in the analysis. Now, if we look at everything else, here nuclei are well separated. Their masks are a bit large, but doesn't matter because we just want to identify where the RNAs are. So it's fine. Now the main problem, everything is good except here, where we have only 3 nuclei and now we have 4. So it's not too bad. But we can see if we can, maybe we can improve that. So let's try first the k-means clustering. So if I go to segmentation, k-means clustering, I can try with, so ideally it would be just 2 clusters, object and background, but here we see that we're missing quite some parts, so it's not good. Let's try with 3 clusters, segmentation, k-means clustering, 3. So it's better now. But it's very similar to here. We're gonna end up with the same problem here. We have one big structure that's gonna be split into 4, unfortunately. Let's just try one last k-means clustering, because when we increase, maybe it can help. So with 4 clusters now, that's not gonna help. So that won't help. Let's try something else. Maybe we can try a scale-based approach. Let's do a difference of Gaussian. So I'm going to duplicate twice. One for, so image, duplicate, sorry. One with Gaussian blurring of 10. Image duplicate, Gaussian blurring of, so here the nuclei are pretty large. We can use 3 or 4. Let's try 3, for example. So I'm going to filter them now, Gaussian blur of 3. All right, I'm going to select the other one, filters Gaussian blur of 10. Now I'm going to do the difference. So process image calculator GB3 minus GB10. Subtract here, and 32-bit because we're going to have negative values. Alright, and when you look at this, you see that it's not going to be very easy to do. So let's do. Okay, and you see either we have background. If we don't have background, then the nuclei are really partial, and it's just if we go back, you can see it from the beginning. If we go back to the image, it's not like we have, first of all, nuclei of the same size. We have small nuclei, we have big nuclei. We have lots of structures in the nuclei. That's going to mess up too. So even if we blur quite some, this are structures that are pretty uniform, so they are pretty low frequency as well. And so a scale-based approach won't work really well here. So now we can try a level set. So I'm gonna go to segmentation level sets. Oh, and I forgot to define a starting point, so sorry. Let's define a rectangle surrounding the image. Go to plugin segmentation level sets. So I'm going to use level sets. I'm going to use expands to inside. And I'm going to use the default parameters here because it should be more or less appropriate. It's an 8-bit image. So let's see what it gives. And I'm going to speed up the video so you don't have to wait the entire process. Alright, it's down. So as you can see, it's not perfect. We identify more or less all the nuclei, but sometimes in very small size. So obviously this is not going to help much. Then, again, I'm not an expert with level sets, and another parameterization might be successful here. But as it's not great with this one, we're going to move on. So we're going to try something we haven't tried last time, which is machine learning algorithm. So if you go to plugin segmentation and trainable Weka segmentation, you have an algorithm that allows you to apply random forests. So which is a more traditional machine learning compared to deep learning, for example. But the advantage with random forest is that you don't need lots of data in your training dataset to get satisfying results. And so the good thing with images is that you can just annotate your image and train your classifier directly with the data you just annotated, the pixels that were considered for one or another class, and get directly the results. And given the results you get, you can update your training dataset and doing iteratively in a way so you're satisfied with your results. Of course, when you train when you have a classifier that you think is good for your data, then you can save it and you can batch process other images. So in this case, so the algorithm is going to try to classify each pixel as part of the object or part of the background. So we define two classes, one for the object. So let's annotate some pixels. So let's take, so this is a pretty easy to define nucleus. We can try nuclei that are maybe harder to get, like this one with dark holes inside, and this one too, for example. So now what you need to understand is that it uses intensity, but it uses also other image features such as texture, for example. So it should be able to identify higher level image structures than something that is just based on intensity, like a simple thresholding, for example. So now that we have defined pixels for the foreground, for the background, let's train the classifier. So it's trained and it's gonna display the results. So the result is overlaid on the initial image, so you can get rid of it. If you want to look at the image, you can get it back. And here clearly we have way too many pixels in the background, so we're going to start to go in regions that are harder, especially between nuclei. So let's add this to the background. Let's add, for example, this to the background. Let's add, so we know that here we had a trouble, we were in trouble when we used the threshold link, so let's directly add something that is in between those nuclei. Let's train it again. And now it starts to look better. So we have those spurious, it's just around the nuclei. I'm gonna just put it in the background as well, and maybe we can separate those two. See if it helps. The thing is that we might get partial nuclei. So again, we can use mathematical morphology. So that's that's not automatically a problem. Here it might be too drastic, especially here when we have those kind of dents into the nuclei. So let's add some. See if it can help. Here it's maybe in between, but let's try. We can classify. So train again. All right. So now let's see if we take this result and with some mathematical morphology, can we get a good segmentation? I think we can try now. Maybe we could add a little bit more, but let's try it. If it doesn't work, we will go back to it. So I can create a result. And I'm going to put it in gray levels. I don't really like to use this kind of colors. Okay. Everything is lost. So when it's the case, generally it's because you have very low intensity. And as a matter of fact, we have 1 for the background and 0 for the foreground. So first I'm going to multiply by 255. So I have only 0 and 255. And now I want to have my object as 255 and background of 0. So I know what I do when I do mathematical morphology. So I'm going to invert, edit invert. All right. So maybe a first step is to fill the holes, because it seems that it's gonna just assign pixels that are part of the nuclei, so that should be fine. So if I go to process binary and fill holes, so I cleaned it up. And now if I use a watershed directly, will I get the right result? Maybe. Let's just try it. Process binary watershed. So almost. You see, now we have the right results. Everything fine, everything else is fine. But here we separated this one into 2 and this one 2. So we need, so I'm going to go back. Generally you can always go one step back if you type Ctrl-Z. So I need to fill this dent and fill this dent. But first, maybe I want to get rid of these spurious pixels, and I can do it with an opening. So I'm going to do process binary open. And maybe it's not enough. You see, we still have some. So I'm going to go back. And when you do mathematical morphology, you can control how much you do it, I would say. How drastic the effects are. If you go to binary and option, you see here you can have several iterations. So instead of doing 1 dilation, you do 2 dilations, for example. So let's change it to 2. And now if I do an opening, I should get rid of everything I don't want to have. Binary open. Okay. That looks better. Now if I do a watershed, I'm going to still have the same problems. I can try it again. Process binary watershed. And you see again this one and this one. So I'm going to go back, Ctrl-Z. And how can I get rid of this? So there's 2 ways to do it. Either I try to close it, or I just do a dilation. So let's try to close it. So if I go to binary close, I close them. So that might be good enough. Let's try the watershed again. Process binary watershed, and I think we're good. I think we're good now. So if you look at it, here we have a 3, here we only have a 3. Oh no, we have this one, sorry. So let's go back. So here, this is not right. I guess if we just do, so let's try a dilation, process binary dilate. We still have enough here to separate, so that should be fine. Let's just try again, process binary watershed. No, so here we have it again, and here we have it again. So, so that's, you know, this kind of shapes are the tricky ones because it's almost okay, but we just have something we don't want to have. So what can we do? We can try again a dilation. Here it should still be fine. So let's see if it works. I hope it's going to work, because otherwise I think we're going to have to go back to what we had before. If I go to process binary watershed, no, this one is very stubborn. So that's bad because everything else is okay, but this one is not. It's just, I guess that's, this doesn't. Let's have a look at the distance map. So if I duplicate this and I do process binary distance map, yeah, so we have those two. Yes, it's because we have those two local maxima. Where can I look at the process find maxima? Yeah, it's weird, but I guess that's what it is. Yes. Yeah. I have those two that's separated into two. It's really not, it's probably also because of the orientation. So the problem is that if we dilate again to try to get rid of this inflection point, it's not gonna help because we're gonna fill in the hole. Maybe you can try if we go to binary, we change to 1, do it, and we do a dilation, and we do, I don't think it's gonna, yes, it did the trick. It did the trick. So you see, sometimes it's really, it doesn't, it depends on almost nothing. So now we have what we want. So probably it would be good to go back to the results out of the machine learning and to do a better chain of mathematical morphology operations to have something that is more robust, because again the idea would be to apply this to many images, and here you see with the number of dilation we made to get rid of this separation is something that is too sensitive, and I guess if we had a similar image we could get into trouble. The other possibility would be to keep going with the classification. Maybe so say this classifier, open a new image, train with this classifier, and then improve on the other image. So we're not too close to this image, and we try to not to overfit, what we call in machine learning overfitting the data. All right, so now that the nuclei are segmented, so we have these ones, and as I said, based on size, we could get rid of them as a post-processing step, and everything else looks fine. So now we're going to take care of the two of the channels. So it seems here that thresholding might be enough. So if I go to image adjust and threshold, and you see with a max entropy, for example, it looks fine. But something I wanted to show you is to use a scale-based method, another one, the log, the Laplacian of Gaussian, which is a very powerful method when you want to segment particles, for example, intracellular particles that are, even if you have lots of noise, it's very powerful when you have this kind of small structures that can be in a noisy, cluttered background. It's also helpful for fish, even though fish generally has a good contrast and just thresholding method could be enough, like in this case. But we're going to try this. So we're going to apply a log. Fiji doesn't come with a log, so we're going to download it. So I'm going to save this image as masks. And we're going to close because we need to download the plugin and then start again Fiji. So I need to close everything. I'm going to download the log. So log, I know that Daniel Sage developed a plugin for ImageG a while ago. So this is the page. You can directly download the zip file here. Let's close this. Let's open an Explorer. We go to download. We unzip that. All right. I'm gonna copy that in the plugin folder of Fiji. So I go to Fiji plugins, paste. And now I can start again Fiji, and I'm going to have the log filter. So I'm going to first open the image, split the channels, image, color, split, and I'm going to apply the log. So channel 2, plugin, log3d, and let's use this size for the Gaussian kernel. Alright, it looks pretty neat. If I threshold, and I would say a stringent threshold again, like the so default work fine. I would say the max entropy works fine too. Apply. Alright, so we have this is the green channel. Let's do the red channel now. Is it a mask? Yeah. Just change the color, sorry, I wasn't sure. So if I go to plugin, log3d, same size, okay. I'm going to apply again max entropy, apply, convert to mask, and now I'm good. I'm going to open the mask I saved, and I'm going to merge the channels. So thresholded log of C1, thresholded log of C2, masks here. Alright, and as you can see, we get the results. So now, so we can associate the particles that are in the fish, so the RNAs either for RB2 and MYC with each nucleus. But sometimes you see, like in here, it's far away, so it's probably not a good one, but here they probably belong to this nucleus. I don't know, we would have to go back to the image, but it's a possibility. So just to know which nucleus the particles belong to, the RNAs belong to, we could use a Voronoi. So let's split this again, image color split. I'm going to duplicate this one, image duplicate. I'm going to apply a Voronoi, process binary Voronoi. Alright, I'm going to put it in gray levels, look up tables, grays. I'm going to threshold it. I don't want to threshold, sorry. I want to change the contrast. So it's going to be image adjust brightness. Yeah, that's what I want. Alright, and now I can combine everything together, image, color, merge, that's right, and no, that's not right. This is Voronoi, this are the masks, and I guess now we're good, just need to change the contrast, and that's it. So as I said, this would disappear as a post-processing step. And now when you have so like these guys, you would say, okay, so they're not in this mask, but they're in this Voronoi cell, so they belong to this nucleus. And obviously we would have to apply another constraint like this one. So with the Voronoi cell belongs to this nucleus, but definitely seems to be quite too far from this nucleus, so probably it's just noise. So we'll see next week how we can do this kind of quantification. Here, you know, the preliminary analysis, which is to identify all the objects of interest, is done through this series of segmentation. And now when that is done, you can go to the quantification.